So today we're going to be talking about the problem of collinearity in a linear regression context. And we've actually been alluding to this problem at various times throughout the semester, but we're going to formalize the concept today. So we've talked about the fact that when the columns of our X matrix are linearly dependent, then X transpose X is singular, which basically means that it's not invertible. And because of that, there's no unique least squares estimate of beta, our regression coefficients. So you may remember that the way that we estimate beta is via beta hat, which is X transpose X inverse X transpose Y. And the problem when we have columns of our X matrix that are linearly dependent is that this matrix right here, X transpose X, is not invertible. And because of that, you can't solve for beta hat using this formula. However, what that does not mean is that there are no solutions. In fact, we have the opposite problem. There are infinitely many solutions. There's no unique solution to the value of beta hat that would minimize our residual sums of squares. So because of that, this is an issue. We don't like it when the columns of our X matrix are linearly dependent. However, we can, even when the columns of our X matrix are not exactly collinear, there's not exact linear dependence in the columns of our X matrix, we can still have problems with estimating our regression coefficients. And so we're going to talk mostly about that in what follows in the rest of this chapter. So in general, if the columns of your X matrix are approximately linearly dependent, so basically the columns of X are approximately linear combinations of one another, then we say that this is collinearity. And what collinearity does is it leads to really imprecise estimates of our regression coefficients. And so practically what happens is that the signs of our coefficients might be different from what we expect them to be. So we might be expecting a positive sign. So maybe if we were looking at the relationship between study time versus study time, the amount of time you spent studying, and then exam score. Well, if we fit a model with these two variables and we saw that the relationship was negative, that would be very unexpected. And in situations where collinearity is present, you sometimes get relationships like that. You're expecting a positive relationship, but the sign of your regression coefficient has an estimated negative value. And so this is a practical problem that we don't want to have to deal with. Another problem that collinearity leads to is that the standard errors of our estimated regression coefficients become inflated. And because of that, it's difficult to even really determine the effect of the regression coefficient on the response. And so if you remember, the standard error is the standard deviation of the sampling distribution of our estimator. And a large standard error essentially means that you have very imprecise estimates of your parameter of interest. And so we don't want to have large standard errors if possible. And collinearity leads to large standard errors, so this is a downside, something that we also don't want to deal with. Lastly, your fit becomes very sensitive to measurement errors, or just even small changes in your responses. So if you change your response vector just a little bit, that can lead to dramatically different values of your estimated regression coefficients. And we don't want to have to deal with this when we're fitting a regression model, because we want stable estimates that we're confident are going to be good estimates of the true relationship between our response and our regressors. So if our model changes a lot with just small changes in our responses, it makes it very difficult to have confidence in our inference and in the conclusions that we draw from our analysis. So those are some of the problems that we can experience when we have collinearity in our regressors. But how do we detect collinearity in practical ways? So the simplest method, and the one I'm not going to recommend for you, even though we'll talk about it, is to simply look at the pairwise correlation matrix between the regressors. And here's the idea. So if we have two regressors, let's just call them x1 and x2, if they are linearly dependent, then x1 is approximately some constant alpha plus some constant alpha 2 times x2. Okay, so if x1 is a linear combination of x2, or at least approximately so, then it's going to have a form like this. And what this practically means is that if we plotted them, if we plotted x1 and x2, we're going to see something like this. And in a plot like that, we can see very clearly that the correlation between x1 and x2 should be quite large. So one of the simplest ways of assessing whether there's a collinearity problem in our data set is to simply look at the pairwise correlations among all the regressors. And when I say large, it's very subjective. It really depends on the context. But if you see large values like 0.9 or 0.8 in your pairwise correlation matrix, that's evidence of a problem with collinearity in your data set. Another tool that people use is actually looking at the coefficient of determination among your regressors. So we're going to let Rj squared denote the coefficient of determination when regressing regressor xj on all the other regressors. And because we have lots of different regressors, presumably, we can compute this Rj squared value for each of the different combinations of regressors. And this really just extends the idea that we were previously just looking at. So if we have multiple predictors or multiple regressors, so let's say we have x1, x2, x3, and x4, though of course we can extend this to more regressors if we want. And if there's a problem with collinearity among our regressors, then for example, we might have a situation where x1 equals alpha x2. Actually, I should use the same notation as before. So it's alpha plus alpha 1 x2 plus alpha 2 x3 plus alpha 3 x4. And so you can see here that x1 is a linear combination of the other regressors that are in our model. And this doesn't have to be exact here. There can be an approximation. It can be an approximate relationship. But the point is that x1 can essentially be written as a linear combination of our other regressors. But if you look carefully at this, this looks a whole lot like our regression equation. So normally we would have a y there, but otherwise this looks exactly like a regression equation using x2, x3, and x4 as regressors. And that's actually the idea with this Rj squared value. And so essentially what we do is we regress, in this case x1, on all of the other regressors, and we compute the strength of the relationship between them. So we compute the coefficient of determination for this model, and that would give us R squared 1, the coefficient of determination for the model that regresses x1 on all the other regressors. And of course, we can swap out x1 for x2, x3 for x1, and so on and so forth, and we can actually get, what we would get was we'd actually get p minus 1 Rj squared values. Because if you remember, in general, we have p minus 1 regressors in our regression model. So we'd have p minus 1 Rj squared values. And if some of them are quite large, that's evidence of collinearity. So that's very intuitive and natural, but it's actually not the statistic that we use generally to identify collinearity in our data. So in fact, what we're going to use is something called the variance inflation factor, which we'll introduce in just a second. But this helps us to understand why collinearity makes it difficult to estimate our parameters precisely. So let's define Sxj to be the sum of squares between, essentially what we're doing here is we're taking the jth predictor, we're subtracting off the sample mean, or I should say the jth regressor, we're subtracting off the mean of that regressor, and we're squaring all the deviations, all the sum of those squared deviations over all observations. And you can actually show that the variance of beta j hat, so the variance of your jth regression coefficient, is equal to sigma squared, where sigma squared is just the variance of the errors, times 1 over 1 minus Rj squared, where Rj squared is the value that we just introduced on the previous slide, times 1 over Sxj xj. So this is a measure essentially of how spread out the values are for the jth predictor variable. And the idea is that if xj does not vary much, then Sxj xj is going to be small. Okay, so basically if the values in the jth regressor do not vary a lot, then these deviations are going to be small. When we square them, they'll still be small. And when we sum over all the observations, they'll still be small. But because 1 over Sxj xj, or Sxj xj is in the denominator here, if this is a small number, that actually inflates the variance of our estimated value for beta j hat. And so if we have very little variability in xj, our jth predictor, our jth regressor, then this can actually inflate the variance of our estimate. And you can see that the same formula here involves the rj squared value, though it actually is 1 over 1 minus rj squared. So the idea here is that if there's a strong linear relationship between the jth regressor and the other regressors, then this value right here is going to be close to 1. And if this is close to 1, that means the denominator is very small, which would lead to a large number here. So just, if you need to, maybe we should just do this. If we're looking at 1 over 1 minus rj squared, let's say that rj squared is a very large number, like 0.99. So there's a very strong linear relationship between the jth regressor and all the other regressors. Well, if we plug that into our model here, we get 1 over 1 minus 0.99, which is 1 over 0.01, which is 100. Okay, which is a very large number. So when we multiply that by sigma squared, we're going to get a very large estimated variance of beta j hat. So if rj squared is large, this is a problem. Of course, if your regressors or predictors are orthogonal, then rj squared is equal to 0, which is going to minimize the variance, which is also another reason why, when possible, we like to design our experiments so that the predictors or regressors are orthogonal to one another. So, practically speaking, what this means is that if we want to reduce the amount of variability, we want to reduce the variance of our estimated regression coefficients, then we want 1 over 1 minus rj squared to be relatively small. And so what we're going to do here is we're going to define something called the variance inflation factor. And the variance inflation factor for the jth regressor is going to be 1 over 1 minus rj squared. So if that number is large, so if the VIF value for the jth predictor or jth regressor is large, that means that we're getting poor estimates of that particular regression coefficient. And so when we compute the variance inflation factor, we generally say that if the VIF value is more than 5 or 10, that indicates a potential problem with collinearity for that particular regressor. You may be asking yourself, well, let's say that I do get a large VIF value. How could I possibly identify which regressors are linear combinations of one another? And that was actually said slightly earlier in the slide here. So essentially what you would do in that case is you would take that jth regressor and you would manually regress it on all the other regressors in your model, and you would simply look for the regressors that had significant regression coefficients, because that would mean that, practically speaking, the regression coefficients for those particular regressors are non-zero, meaning that those are the regressors that are linearly related to predictor xj. So just to be a little bit more specific there, if we regress xj on the other regressors, so we'll have alpha plus alpha 1 x1, we'd skip the jth one in here, but then eventually we'd get to alpha p minus 2 x p minus 1, because normally we have p minus 1 regressors in our model here. Okay, and the reason why I have p minus 2 here is because one of the regressors is actually over here. Okay, so this xj is over here. It's not going to be in this linear combination. And so some of these might not be significant. So for example, this one might be significant. All the other ones in between are not significant. But then this one is also significant. And essentially, if the regression coefficients here are significant, the alpha 1 and the alpha p minus 2 are significant, that means that these values are non-zero and xj is linear related to x1 and xp minus 1. So just going back to this slide right here, if we're trying to identify which regressors are linear related to one another based on the variance inflation factor, we would identify the regressors that have a large variance inflation factor, and then we could, if we wanted to, regress that regressor on all the other regressors and figure out which coefficients are significant. And that would give us an idea of which linear combination is problematic. The last way that we're going to talk about identifying collinearity in our model, and actually the best way, in my opinion, is looking at something called the condition numbers. So what we want to do is we're going to compute x transpose x, usually after removing the intercept or after scaling our predictors, which means that we center them, we subtract off the mean and divide by their standard deviation. Then we're going to look at the eigenvalues of x transpose x. And after we do that, we're going to compute lambda 1, lambda 2, up to lambda p minus 1, where each of these lambdas, so these eigenvalues are ordered from largest to smallest, and what we're going to do is the condition number, we're going to compute the condition number, kappa, which is the square root of lambda 1, the largest eigenvalue, over lambda p minus 1, which is the smallest eigenvalue in this ordered list right here. And if that condition number is more than 30, that indicates a potential problem with collinearity. However, we can compute other condition indices. There's actually a typo here. No, there's not. Sorry, there's not a typo. The other condition indices are going to be the square root of lambda 1 over lambda I. And so for the one where we're using lambda p minus 1, that's going to be the largest condition index. That's going to be the condition number. But the other condition indices are actually useful as well, because if you have multiple condition indices that are more than 30, that indicates that there's more than one linear combination that might be causing problems with collinearity in your data set. So once you compute this condition index and you identify whether there's a problem with collinearity, you can actually use something called variance decomposition proportions to identify which linear combinations are causing problems in your data sets. And so we're not going to go into all the process of how this is computed, but we're going to use a function in R to compute these variance decomposition proportions, and you're going to see that they're going to be matched up with the condition indices. And so for each one of the large condition indices, you're going to look at the variance decomposition proportions. And if you have two or more regressors that have large variance decomposition proportions, like say more than 50%, then you should probably remove at least one of those regressors from your model, because essentially those regressors are playing the same role. They're highly correlated with one another. They're linear combinations of one another. And so the function that we'll use to do that is the call diag function in the perturb package, and it's going to compute both the condition indices as well as these variance decomposition proportions. And you may be wondering, well, what if I get a large condition index, but only one of the regressors in my variance decomposition proportions has a large proportion? Well, if that's the case, don't worry too much about it. We don't want to be overzealous when we're removing regressors from our model or considering them for removal. And so you really want to focus on the condition indices that have more than one regressor with a large variance decomposition proportion. And we'll actually see that in an example shortly, so to make this a little bit more concrete. So just to kind of summarize what we just talked about, the different methods that we use for identifying collinearity in our regressors is looking at large pairwise correlations. Okay, that's not really recommended, but you can do it. A much better method is to look at the variance inflation factors, identifying regressors that have values more than, say, 5 or 10. And lastly, it's a little bit more difficult to use, but even better than the variance inflation factor, is by looking at the condition index in connection with the variance decomposition proportions. That's going to be the most sensitive and the most informative for identifying collinearity in your regressors. So let's do a quick example to better understand how we would identify collinearity. And so we have this driving data set where essentially we're looking at the relationship between characteristics of a person's body type. So for example, how tall they are, how long their legs are, how long their arms are, and where they like to adjust their seat when they get into a car. And the idea is that car researchers want to figure out how to design cars so that people are comfortable when they're sitting. And so this data was collected by the University of Michigan. We have 38 drivers, and we have the subject's age, their weight, their height with shoes and without shoes, their seated arm length, the length of their thigh, their lower leg length, and hip center, which is the horizontal distance of the midpoint of the hips from a fixed location in the car in milliliters. And hip center is actually going to be our response here. And what we want to do is we're going to regress hip center on all the other regressors in our data set, which is in the seat position, the seat pause data set. And so we do that regression, we're going to call that LM1, and I'm going to look at a summary of LM1. And what I want to point out here is that the R squared value is actually reasonably large. It's about 0.7. So the fit of our regressors to the response is actually pretty decent. But if we look at the p-values for each of our regression coefficients, you can see they're all quite large. None of them are even close to being significant. And so if we have a large R-squared value, but then none of our predictors are significant, that is a clue that you might have a problem with collinearity in your regressors. And so even though we haven't done any of the formal diagnostics, this right here, seeing a large R-squared value, but as well as large p-values for all of our regressors, is an indication that we probably have an issue with collinearity in our data set. So in terms of detecting the problem with collinearity, we compute the pairwise correlations of all the regressors, all the predictors in our model. And this actually includes SIP center as well. So this is not just the correlation of the regressors, but also of the response here. And I've rounded these to 3 decimal places so that I can show this all on one slide. So I'll zoom in a little bit here so we can see it a little bit better. So essentially what we're doing here is we're trying to identify large pairwise correlations. Of course, the diagonal elements of our correlation matrix are going to be 1 because each variable, each regressor is going to be perfectly correlated with itself. Then we're looking for other variables that have a large pairwise correlation. So for example, we see that the pairwise correlation between height and height shoes is 0.998. There's almost a perfect one-to-one relationship between those two variables. Even seated and height shoes has a very large pairwise correlation. And you can see there's a number of other ones. We actually have a lot that are more than 0.5 and several that are, we have some negative correlations here, but even that's a problem because a large negative correlation is still a strong correlation between variables. And so we can see just from looking at the pairwise correlations that we see that we have a problem with collinearity, especially height and height shoes, but there's definitely some other ones that we're going to need to consider in our analysis. So now let's look at the VIF values for our data set. And so the way that you can actually compute VIF values is by fitting your regression model, which in this case is already stored in LM1, and then we simply use the VIF function, which is available in either the CAR package or the Fairway package. So it actually doesn't matter which one you use. And so we have the VIF value for each one of the regressors that are in our model, and we can see that height shoes and height have really large VIF values. And so at a minimum, we can see that there's a problem with the height and height shoes predictors in our model. And we already know that they're highly correlated, and this, of course, makes perfect sense because my height and my height with shoes are going to be very similar to one another. There'll be some fluctuation depending on what kind of shoes I'm wearing, but for the most part, if you know my height, you're going to know roughly my height with shoes on. And if you want to interpret this for the height shoes regressor, we might say something like, so if you take the square root of 307.4, that's telling us essentially the multiplicative impact that the correlation, or I should say that the collinearity problem is creating with our estimated standard error. So the standard error for height with shoes is about 17.5 times larger than it would have been if there was no collinearity in my data set. And that's a lot. So that's a pretty substantial change in my estimated standard error because there's a problem with collinearity. So this is a rough interpretation, but the idea is that these variance inflation factors, they really tell us how much extra variance we're getting because of the problem with collinearity, which is why we don't want large variance inflation factors. So the last tool that we'll use to identify or to check this problem with collinearity is to look at the condition indices for our regressors. And so what I'm going to do here is I'm going to take the X matrix for my fitted model, and then I'm going to subtract off the first column, just because I usually keep that in there, so we're not going to worry about that in our analysis. And then I take the cross product of X and with itself. This is the same thing as computing X transpose X. So cross product X here is computing X transpose X. And I compute the eigenvalues of that, and I'm going to store it in this object E. And then lastly, I'm going to take the largest eigenvalue, I'm going to divide it by all of the other eigenvalues, and I'm going to take the square root of that ratio to get the condition indices. And so this largest value right here, which is the square root of the ratio of the largest eigenvalue to the smallest eigenvalue, this is the condition index. Then these are all the other condition indices. And so you can see that we actually have several where the condition index is more than 30. And so it's definitely possible that we have more than one linear combination that's causing a problem with collinearity in our data set. So as I mentioned, though, this simply tells us that there is a problem. We want to identify where the problem occurs. And so if I go scroll down a little bit, I'm going to look at the variance decomposition proportions for the regressors that are in my model. And so I mentioned before that there's a call diag function in the perturb package. And so in order to make this compatible with what we've done before, we're going to use our fitted linear model. We're not going to scale our predictors. That means just leave them the way that they're given in the fitted model. And it asks whether we should add the intercept, and we don't want an intercept. So in our previous analysis, we removed the intercept from analysis. And so when we do that, you can see that the condition index is computed for each of the regressors, and these match up perfectly with what we computed before. And then each row here after that computes the variance decomposition proportions for each condition index. And what we're looking for is we're looking for rows where there's more than one regressor that has a large proportion value, so something like more than 0.5. So for example, if we look at this row here, which corresponds to the condition number, we can see that both height shoes and height have very large variance decomposition proportions. Both of them are actually very close to 1. And so this would indicate that there's a problem with collinearity between height and height shoes. If we go to the second from the last row, where we have a condition index of 262 approximately, as we go across and look at the variance decomposition proportions for the different regressors, we actually only see one regressor that has a large proportion, close to 0.9 here. And so because there is not more than one proportion that's large, we may not worry about collinearity for that particular regressor, at least not based on that condition index. If we look at the third from the bottom row, or second from the bottom, this row right here, row number 6, we see another large condition index. And as we move right along this row, we can see that both the seated and arm regressors have large variance decomposition proportions. So this isn't quite 0.5, which is what I mentioned in the notes, but you can see it's pretty close to 0.5, and this one is more than 0.5. And so it seems like there may be a problem with collinearity between seated and arm regressors, and so we may want to remove one of those regressors from our model before we actually do our analysis. Okay, so that's how we identify. So that's one way of identifying which regressors are causing problems with collinearity. So I mentioned previously that one of the issues with having collinearity in your data set is that if you very subtly change your measurements, you can actually get dramatically different responses, dramatically different estimated coefficients. And so if I take my hip center response and I add a little bit of error here, then the estimated coefficients are actually going to change dramatically. So you can see that we have a bunch of negatives here, where in our original model, okay, we only had a few negatives. And so our estimates changed dramatically simply by adding a little bit of error to our original hip center measurements. And so that's really not a good thing to have. It means that our estimates are not stable. And so we can't really trust our fitted model in that case. And so that's a bad problem to have when we're doing regression coefficients. And what we're actually doing here is, so this is another way of looking at the change in the regression coefficients. So essentially what I'm doing here is I'm looking at a plot of the scale difference in estimated coefficients for the two models. And so I'm taking the difference between the estimates for the two models, and I'm dividing by the estimated coefficient for the original model. And you can see that some of these coefficients are changing by a factor of 4. Okay, so one of the coefficients is 4 times larger than the other. So this is a problem. So we're getting some dramatic changes in some of our coefficients. And it looks like probably the height and height shoes coefficients are changing the most, which is not surprising considering that they were the ones that were most highly correlated with one another. So we're having a real big problem with collinearity in our model fit. So now that we have identified some of the regressors that may be collinear with one another, the question is, how do we solve the problem of collinearity? So I've already mentioned this several times in this lecture, but the simplest approach, and actually the one I like the best, is simply amputating or removing the offending regressors from your model. So if you have two regressors that are highly correlated, then essentially they give you the exact same information and you don't need them both. So if I have height, I don't need height shoes, or vice versa. So removing one of the regressors removing regressors that are in combination, that are linear combinations of one another, is a very straightforward way of solving the problem of collinearity in your model. So something else that you can do that sometimes helps is centering your regressors. And that means what you do is you take each regressor and you subtract each value by the sample mean. So this is a solution, for example, when you're fitting polynomial models. So if you have models that are something like y equals beta naught plus beta 1 x plus beta 2 x squared plus beta 3 x cubed, etc. Okay, then oftentimes as you fit these higher order, as you keep increasing the order of your model, you start having problems with collinearity. And a simple way to correct that is simply to center your predictors. And when you do that, then a lot of the collinearity problems are accounted for. Similar to that, we can scale our regressors, which is dividing by the standard deviation of each regressor. And then standardizing a regressor is both centering and scaling the regressor. So we subtract off the mean of each regressor, and we divide by the standard deviation so that the standard deviation of the regressor is now equal to 1. So those are some simple solutions for collinearity. Another one you may have heard of is the lasso method, which actually shrinks the regressor. The book does talk about this, but it's not something we're going to cover in this course. We're covering the most basic methods for solving the problem of collinearity. So, as I mentioned, based on our previous analysis, we noticed that height and height shoes had very large variance decomposition proportions when we were looking at this table right here. We also noticed that we had a problem with seated, and the seated and arm variables also had large variance decomposition proportions and a high condition index. And so it's a good idea to actually remove one of those predictors at least. So we'd probably remove height or height shoes. We'd also remove one of seated and arm. And after we identify these collinear regressors, what we would do is we'd actually refit the model. And so it's actually an iterative process where you can identify whether there's a problem with collinearity. So after fitting the original model and seeing that there's a problem between height and height shoes, we might remove the height shoes variable and then check again whether there's still a problem with collinearity in our data set. And if there is, then we keep removing regressors until eventually there is no longer a problem with collinearity. One of the things you might notice when you do this actually is that the condition index method, the condition number method, is much more sensitive to identifying collinearity than the variance inflation factor method. And so it depends on who you are about how you want to account for that. So I like to be a little bit conservative, and I'd rather remove a regressor if it's potentially collinear with another regressor, then keep it in the model. Whereas other people say they want the maximal number of regressors to use in their fitted model, and so they'll only remove ones if there's a large variance inflation factor. So that's definitely something that it depends on the person about how they're gonna deal with that. So as we're finishing up here, I just want to show you what we can do here as we remove collinear regressors. And so what I've done here is I've removed several of the regressors, not just height shoes and the arm length, but actually some of the others. But I'm regressing hip center on age, weight, and height. And you can see that after doing that, not all of my regressors are still significant. That's not necessarily a problem with collinearity. But I've removed a bunch of these collinear regressors, and I still get an R-squared value of 0.6. So my model is much, much simpler than before, but the quality of the fit is almost the exact same as it was in the original model. And it's possible that we might even simplify the model further just because we see that, for example, weight seems to have no relationship with the response. So, as I mentioned, we don't always want to amputate regressors. And in fact, sometimes it's strongly desirable not to do that. And so if you really need to keep all your regressors in your model, then there are some other modeling strategies you can use. So one of them is called ridge regression. The other one I mentioned was the lasso method. And these are both forms of penalized regression. But in both cases, what they're going to do is they're actually going to shrink some of the estimated regression coefficients. And this helps to overcome the problem of collinearity. So because we add this penalty in our fitting equation, it makes it so that we can actually invert x transpose x, and we don't have the same estimation problems that we have if we don't penalize the regressor and just do ordinary least squares estimation. So this is actually a really important thing. It's the slide I'm going to conclude on here. So you may be asking yourself, so when should I check for collinearity? So you might think to yourself, well, this feels a lot like a model diagnostic tool, and so I'm going to fit my models, I'm going to do my model selection process, I'm going to do my diagnostics, and then I'm going to check for collinearity. In fact, if you look carefully at the slides that we've just been looking at, collinearity is in no way related to the response variable. You actually don't even need to fit a regression model in order to check for collinearity. It makes some of the computations easier, and a lot of the functions that we looked at actually take the fitted model to compute the collinearity statistics, but you actually do not need to fit a regression model in order to check for collinearity, at least not a model regressing the response on the regressors. So actually, when you should check for collinearity before you even do the model selection process. So after you do exploratory data analysis, so after your initial plots, looking at the general relationship between the response and the predictors and regressors, and looking at the various summary statistics, after you do that, that's when you want to check for collinearity, because you actually want to remove collinear regressors from your model or from consideration before you even start the model selection process. And so for a lot of you guys might remove several regressors before you even begin the real model selection process, which actually makes the model selection process easier. So after you do exploratory data analysis, you want to check for collinearity. And so just to sort of summarize things here as we're wrapping up the semester. So when you're going through the model fitting process, what are the steps that you're going to use? So the first thing you should do is you should do exploratory data analysis. These are plots of your response, these are plots of your regressors, looking at their distribution, how they're related to one another, looking at summary statistics, etc. After you do that, then you want to check for collinearity. And my recommendation is that if you have problems with collinearity, then you remove the offending regressors from your model, whether that's looking at the condition indices or looking at the variance inflation factors. You may be able to remove one or more regressors from consideration. After you do that, then you're going to go through the model selection process, right? So this involves a lot of fitting of various models and things like that. And after you do the model selection process, then you're going to look at the model diagnostics. So are the assumptions that we've been making the entire semester valid or not? And if the diagnostics are not met, then you may need to go back to step 3. Because sometimes the diagnostics suggest transformations of your response or of some of your predictors to compute new regressors. And if you do that, that's going to influence the model selection process. And so after you do your diagnostics, a lot of times you're actually going to go back to the model selection process and come up with a different model. And after you do model selection and assuming that your regression diagnostics come back okay, that's when you're going to start making inference, doing things like prediction, and making interpretation for your regression model. And so some people might vary slightly in terms of how they do this, but this is a general process that I follow. So I want to look at how the data set is organized in general, what are the various properties, check for collinearity before I do any real model fitting. Then I go through the model selection process to identify a good model. I check the diagnostics to make sure that the model I chose is actually a reasonable one, that it meets the assumptions that we need to be met. If not, I go back to the model selection process and I keep iterating through until I get a good model. And then once I have a good model, then I can make inference about my regression coefficients, I can make prediction for future observations, and I can interpret my results.